Okay, so I'm going to head over to the Jamboard and wanted to walk through some of the interactive teaching strategies that I'm familiar with, and there's a lot. So this is definitely a non-comprehensive list of interactive teaching strategies that have been shown to work in STEM. Most of these I'm going to show you have research backing. Some of them are innovative and new and don't yet have research backing, but I think should be useful for student learning as well. If you were here in person, I also have a handout. So that's the handout that was in the email to you that you may or may not choose to use. I'm actually going to pull it up for myself and keep a copy of it to show you how I might use that during class.
Peanut?
Yeah.
I couldn't find the link. Oh, wait, never mind, it's here. Sorry.
Okay, so you should be able to see the on my screen now. Here comes Courtney. All right. Good morning, Courtney.
Hi there.
I'm going to send you some stuff.
Great. I'm clearly not a STEM faculty member, but grateful to be here and support you.
And really, these techniques that we're going to be talking about are not specific to STEM necessarily. They're just useful teaching strategies.
Yep, all good. Thanks for doing it.
And so your inbox has a handout. I'm also going to stick in the chat link to this Jamboard up on the screen. Sean as well. Good morning, LaShawn. LaShawn, do you want to give a quick pitch for your workshop in a couple of weeks?
Sure, I don't mind. So within a couple weeks, we'll do perhaps this or very similar to this again. And my emphasis will be more on the social services. I'm sorry, not social services. I'm catching my breath. Coming from a different angle other than math and science. I'll say that as a general statement. I look forward to hosting in person, of course, as well as online. For the in-person experience, and I'm going to try to, for the most part, capture the same or a similar experience from an online perspective. My goal is to give the tangibles. So for those that are in person, I want to, again, create an experience centered around what most often happens in my classroom, centered around a more tangible learning experience when talking about the subject matter.
Great. Thanks for hosting that on behalf of Faculty Development Council. So we're going to go ahead and jump in. I was giving an intro to the others as you were all coming in. That's fine. I understand running around this morning. I was too. So this is a non-comprehensive set of active learning strategies that have been shown to be effective in STEM settings. These are not unique to STEM. So I often take the approach that active learning is just good for everybody, regardless of what the situation is. But of course, I know the STEM perspective best. Coming from the STEM perspective, I'm a STEM education researcher myself, so I appreciate having data about what actually works and using our scientific thinking processes to improve teaching. Okay, so starting off here, what is interactive engagement? As a definition, this is my definition. You may agree or disagree. It's teaching in which students are actively thinking, doing, and practicing during class activities. So that's a pretty broad definition. It's almost anything that's not just the student sitting there listening to you lecture. Not that there's anything wrong with lecture. There's a time and a place for it, and we do have to do some of it regardless. But if we strictly lecture and don't give students time to think and do and practice, then they're not really going to learn as effectively. And I'll show you some data on that as we go. So down here we've got some of the key features of interactive engagement, and I'm abbreviating here. Where it's more focused on what students are able to do with the information they have, not just about transmitting information to them. So we definitely have a long history of teaching as transmission of information. The need for that is less now than it used to be because we have information just much more readily available for students. So they can get the information from places other than us as the faculty members. They can get it from the book, they can get it from the internet, any kind of sort they can do it. In interactive engagement classes, it's not just teacher to student talk. There's also a lot of students talking back to the teacher and students talking to other students. This often ends up creating a very collaborative learning community. If it's working well, everybody is invested in everybody else's learning and trying to do the learning together as a team. Definitely worth mentioning that also goes for diversity, equity, and inclusion. Interactive engagement is not specifically geared to diversity, but it's good for everybody. So it does tend to be reducing achievement gaps, for example, between different ethnic groups. If you want to hear more about that, we have another workshop coming up through Title V that Elijah Roth and I are leading in a couple of weeks. We're going to talk a lot more about how that plays out. In an interactive engagement classroom, students' ideas are taking a more central place rather than just the information from the faculty. So it's important that the students' ideas are respected. They don't come to our classrooms as blank slates. They know some stuff coming in. So we want to respect that. And some of what they know is right. Some of what they know is almost right. So making that distinction can really help with the respecting of students' ideas and changing them to all the way right. We are definitely aimed at 100% success for all of our students. I'm not saying that all of our students will succeed, but that I'm saying that that is our goal. In many cases, that it's just impossible to actually reach 100%, but we're aiming for it always. And we're looking for strongly coherent conceptual understanding and problem solving. So down here at the bottom, I've got a gap. Interactive engagement is sometimes known as, and if you're following along with the handout, I'm going to do some notating on the handout as well. So I might do this in class. I actually typically don't, but several people do to good effect. And we can just write straight into the handout. So I'm going to do a teaching in interactive teaching is teaching in what students are doing, practicing, and I forget what the third one I said. I should have noted this when I did it. Thinking is the third one. Down here, interactive engagement is sometimes known as learner-centered teaching. Rather than instructor-centered teaching. While I'm here, I just want to highlight this here. Good resource for you if you're interested in a kind of a comprehensive guide to interactive teaching in STEM. This has lots of techniques. The math, physics, and statistics department did this book as a faculty reading group and had lots of really good conversations around it. So I recommend that book. A couple of thinking questions for you here. Question number one, question number two. I'm defining some terms here. Ratio is the percentage of the class time that is spent with you as the instructor talking. So take a minute and think about that for yourself. What is your ratio in one of your typical classes?
Peanut, you're asking ratio of student to teacher?
The ratio of what percentage of the time are you talking?
Oh, percentage of time. I'm sorry, I missed the whole point. In my classrooms, I would go 70-30.
70 is you talking and 30 is them?
Yes.
Yeah, that's reasonable. And everybody else, you can answer for yourselves. If you had the handouts in paper, I would tell you write it on your paper. There's not a right answer to this, though I would say if the answer is 100% of you talking, you're probably missing some learning opportunities. Also, if 0% is you talking, you probably have an issue. So somewhere in the middle is probably decent. Mine varies depending on which class it is. Some classes I'm more in the 70-30 range. I have at least one class that I'm in the like 15 to 85 range. That's an honors colloquy, so they take it in mind. Okay, next question. So what percentage of the students are engaged in one of your typical classes? And by engaged, I mean doing something, not just listening or staring into space or turtling around on their computer. What percentage of your students?
If I do have class activities, then like everybody will be engaging because they're forced to.
Okay. They still could not. It might be socially unacceptable to not engage when you have those activities, but that's good. So ideally on this one, I would say that there is a correct answer. We want it to be 100%. We don't always get there.
Mm-hmm.
And that is tied back to this, aim for success of the 100% of the students. So if your percentage of students who are engaged is less than 100%, you're probably not going to reach 100% success. Okay, moving along. I'm heading back over the slides for a minute. So this one is a graph that I became aware of a long time ago. This is from a physics education research paper way back in 1998. This is pretty foundational paper, a lot of physics education research. So walking you through this here, what we have is a histogram. So this axis is which fraction of courses in the study. This thing here is called the normalized gain, which I need to define for you. In order to get the normalized gain, what he would do is there's a standardized conceptual understanding test that's used in introductory physics courses around the country called the forced concept inventory. It's given as a pre and a post, so you can measure gain during the semester. And normalized gain is the gain over the maximum possible gain for that student. So if a student got 10 out of 30 right on the first test, then their maximum possible gain would be 20. And say that they actually improved to a 17 on the post test, then they would have got 7 out of 20 normalized gain is what this is giving. And these are class averages for number of courses. On this histogram, you see that there's two different colors. We got the white bars and we got the black bars. The difference between those is the white bars are traditional lecture courses, and the black bars are interactive engagement courses. So I wanted to ask you all on this, what do you notice from this graph? I'll call on somebody. Lou, what do you see?
Yeah, so for the black, let me see, interactive. Yeah, so when we have interactive engagement classes, then the gain would be higher, right? I think.
Yep, that is the big punchline.
Mm-hmm.
Yeah, black, the average is somewhere around here. About 50% of the possible learning happens. I still would like it to be higher. But if we're looking white, the average is right about here. 24%. Ouch. So if we're just traditionally lecturing, they're not learning very much of it. That's a problem. I ran across this my first year of grad school. They showed this to us as grad students and said, we need to do better than 24% of our learning if we want to actually have people proficient in physics. Okay. You may also notice there's more of a spread in the black. And there's the white. The white, it doesn't matter what you're doing, they're going to get the same thing. But black, there's more of a range of different types of interactive engagement that are going on, as well as more of it is on the students. So the student response to it has a bigger effect on the learning. Okay, so I'm saying interactive engagement matters because they just flat learn more if we do it. And that's what I'm after. Okay, I think I'm going to skip this for just time's sake, but these questions are on your handout for your thinking. Cruising right along. This one I'm going to go really briefly. These are not evidence-based, really, I don't think. This is more conceptual graphs comparing traditional lecture to lecture with activities. Just percent of students in the classroom are attentive versus time from the beginning of class. So when you start class, for a little bit, their attention actually tends to go up because they're getting settled. They just did the run over from the other campus. And once they have themselves oriented, then they start to focus a little bit better. So there tends to be like a maximum in their attention about 10 minutes into class, but then it tails off. And this happens for us too, as faculty. It's hard to pay attention for an hour or an hour and a half or 3 hours classes that we sometimes have. That's just not the way that our brains work. Focusing that long is not very effective. So this graph is coming from that book that's on the handout, the Teaching and Learning in STEM Practical Guide from Felder and Brent. They're recommending doing a series of activities throughout your class and mixing it up so that every time you change an activity, that's a time for students to reset their attention. They can get their attention focused back. So student attentiveness can be maximized by frequently changing activities. If you were in person, I would tell you to write that on your handout. That's all right. Okay, moving along. So the rest of the time I wanted to take some time to walk through some interactive engagement teaching strategies and practice with them. Again, this is not a complete list, so this is just ones that I've seen used effectively here at Indeed. My go-to is peer instruction. I use this in almost all of my classes, almost every day. And this is the routine that goes on in peer instruction. So you pose a question. For me, that's usually projected up on the screen. I'll show you one in a minute. The students then think silently and come to their own individual answers on it. At that point, I ask them to vote, and I ask them to vote all simultaneously. So everybody's voting, everybody's telling me what they think. Because it's simultaneous, they can't wait for somebody else to answer and copy off of them. Then I very often will say, turn to your neighbor and convince your neighbor that you're right. You have 1 minute, go. And they talk and it gets crazy. During that discussion, they may have incorrect answers, but they're talking to somebody who might have a correct answer. So they'll walk through it and sometimes they convince them and they change their mind. Or at least they'll get more practice in talking about the physics that I'm after. Then we revote in order to give them that chance to change their idea. And then we'll do a discussion as a whole class about what the reasoning should be and what the answer is. So true or false question, peer instruction must use technology such as clickers. These are sometimes called clicker questions by some people. What do you think, true or false?
False.
False? Why is that false?
Peer instruction, you mean the vote stage, right?
Yeah.
The voting stage? The voting stage, I sometimes ask them to just show their hands because I don't actually use clickers. I don't know how to use it.
I don't use clickers either. Lots of people do, and there's advantages to them, but there's also disadvantages. To vote, you need some way that they're showing the instructor what their answer is, but it doesn't have to be technology-based. For years and years, I used little paper flashcards that they would show me. Now I'm usually just say, just use your fingers and show me with your fingers. That gives me enough information. I do tend to shy away from raise your hand because then everybody else sees what their answer is, and that puts peer pressure. So if they're doing fingers, they can just show me like this, and it's between us.
Okay.
That's a small detail, doesn't really change the effectiveness that much, but okay, so let's try one. This is a peer instruction question from about halfway through my introductory physics course, and I picked one that I think you might know something about. So there's the question, take a minute, think about it, and then select your answers. Do you need more time? It's a no pressure, of course. And I never grade these. These are formative. So if it was in person, I would ask people to use their fingers to show me their answers. Since we're online, I'll show you how to do it in that case. Everybody put your answer in the chat, please. Ooh, interesting. We have a disagreement on this one. I'm not surprised because I intentionally chose a question that was going to lead to some discussion. Just for time's sake, we're not going to do discussion, but at this point I would say, turn to your neighbor, convince your neighbor that you're right. Your feelings are valid, Courtney. And then I would explain. Sometimes I actually use my learning assistant to explain for me. Sometimes my learning assistant and I play good physicist, bad physicist, where one of us gives correct answer and one of us gives almost correct answer. We can talk about what's not quite right about it and play that fun game. Okay, so I'll talk through the answer on this one, just to not leave it hanging. Answer this one is actually none of the above. The reason why is the moon is in Earth's gravitational field, that's true, but gravitational fields make things fall. So that's the opposite of what the answer would be. So not that. Net force on it is 0. This is also not true because there's one force acting on it, that's the gravity. I don't have anything to balance that, so the net can't be 0. It is beyond the main pole of Earth's gravity. That's just false. There's definitely Earth's gravity extends off forever. It is true that it is also being pulled on by the sun and the planets as well as the Earth, but that's not making it fall to the Earth. And those are smaller effects because they're really far away. All of the above are definitely not true. None of the above are true. The moon is within Earth's gravitational field that pulls on it, and that makes it fall. It's actually always falling. It's just falling and going sideways fast enough that as it falls, it goes in a circle. So the answer, of course, doesn't matter for your purposes, but that's how I would kind of walk through it in class. That was the fast version I would take time to class. So I'm going to go fast on this as well. Pros and cons of peer instruction. I really like peer instruction for answers that require conceptual thinking. In my experience, it doesn't work as well if there's numerical answers. Process answers also work well on these sorts of things, like what step should I do next? You do want to give questions that are at the right level so that there's discussion to be had. If they're too easy, then they all just look at each other and say, yeah, what did you get? Okay, that's right, I agree. And then the conversation is over. You don't get that deep thinking that goes with the discussion. Or if it's too hard, if everybody has totally incorrect answers or everybody is feeling as inadequate as Courtney shared with us, then you also get not very good discussions because there aren't enough ideas to share. So there's a sweet spot to be had there. Usually I'd say about 50 to 75% of them getting it correct on the first vote is where I want to aim my questions. I do these as I'm going. So I intersperse them through the lecture. I'll do like mini lecture, peer instruction question to check that they're understanding me. I like that every student answers. At least they have the opportunity to. I always am struggling with a few of them who don't want to stick their neck out and answer. And if that student is being really reluctant, I might pull them over after class and say, what's the barrier here? Why are you not answering? Let's talk about the emotion that's going on that's keeping you from answering this question that has no stakes. These can go pretty quick. About 5 minutes per question is pretty normal. So I can do a lot of these in an hour if I really, really want to. I usually don't do an entire hour of them. This can go wrong if your questions are too easy or too hard. It can go wrong if some students are refusing to answer, but then you can talk about it and say, please answer, it's good. It can also go wrong if not everybody is answering at the same time and some students are answering and then everybody else is looking at what they answered and then just copying it. So this is why I'm avoiding that hand raising most of the time. And I actually tell my classes, don't answer as soon as you have an answer. Wait until I tell you to answer so everybody is answering simultaneously. That helps prevent this copying effect. I'm not going to talk about these down here, but these may be some other things that are kind of similar. Bell ringers are almost like peer instruction questions that just happen at the beginning of class to review the stuff from the previous class. Think, pair, share is still students talking to each other after a question is posed and then sharing back. In some ways, just instead of multiple choice questions like that last sentence for more open-ended questions. Maybe worth mentioning as well that I have used peer instruction without doing multiple choice. In those cases, I had students with like personal whiteboards and they'll just write down their answer and show me on the whiteboard. Works well too. Buzz groups, also more open-ended questions, pretty similar to Think, Pair, Share. Good physicists, bad physicists, that one I mentioned already. Questions about peer instruction before I cruise along, I'm going fast. All right, next technique. This one I actually just learned last week as I was doing a class observation as part of the NSF grant supporting LAs. One of our learning assistants suggested this to his faculty member, and they've been doing it in a Chem 2 class. So Taboo, you might have played the parlor game Taboo. We're going to do that, but academic. So how it works is you write terms from your discipline on cards. You hand out those cards to groups, and then you go around the group and each person takes turn trying to explain their term without using the words themselves. They're verbalizing the concept behind these academic vocabulary terms. And we keep doing that for as many terms as we have. So let's give it a shot. I pre-prepared some, and I'm going to get my cards. And since many of you registered, I know who is coming, and I picked terms from your discipline. If it was in class, I would just hand out the cards to you, but since we're in Zoom world, I'm going to send you personal chats with some terms. All right. So be looking an eye on your personal chat. Edwin's. Let's go with LaShawn's. Let's give one to Lou. Courtney, do you want one?
I'm good to observe.
Okay, for time's sake.
My only hope in getting this right is maybe LaShawn. I think Edwin and Lou, I'm going to be outside of my depth.
We'll try. Okay, Edwin, you get to go first. Try and describe your term to us.
It has something to do with addition, subtraction, multiplication, division, and then moving things around.
Algebra?
What was that?
Algebra?
Yes.
Okay, algebra. We got it. Lou, since you got it, you get to go next.
Yeah, so suppose you write a program in Java, and then you want to run the program on your computer. So we have to basically translate the Java statements into the instructions that the machine can understand. So this is the term I'm describing. There is a verb. It's a verb, basically converting the high-level programming language statements into statements or instructions the machine can understand. I think it's too technical for non-CS people, maybe.
Coding?
It's not coding.
That would be the writing the code step. She's asking about the step that makes it runnable.
Oh,
Edwin should know this one.
I'm embarrassed. Compile?
Yeah, compile, yes.
Yeah. All right, LaShawn, you want to try yours?
sure. Just for a point of reference, if it's okay to say this, that I'm in the School of Business and Management. So the way that which I would describe my term is the original sum that's invested, an amount of money that is lent or invested, and which interest is paid.
You can't see the grimace on my face, but is it principal?
Yes.
I'm not a business person. I'm just an adult.
That works. It is principal.
So you all are much better at this than the students are, but it's a challenging task, right? To try and put it in conceptual words without using the exact term. As students are doing this, they're doing really serious thinking about the meaning of this thing. It's what we're after. So I think that this worked pretty well when I observed it in class last week. For the blank here, for maximum usefulness, taboo descriptions must use terminology from the discipline. So if, for example, LaShawn had said, the guy who is the boss of the elementary school, we could guess it that way, but it's not going to be really engaging with the discipline in the way that we want. So good, thank you for playing along. So this is good for building conceptual understanding, especially in classes where vocabulary is a big deal. So I'm skeptical whether it would work that well in a math or physics class, but it does work in plenty of other STEM fields pretty well. The students, when I observed this last week, loved it because it was gamifying the class for them. And they were very interactive about it. It can go pretty quick. You just saw how fast it was going. That was probably less than 2 minutes per term, because you're good at it. You've explained these things to lots of people. If students are doing it and they're struggling a little bit more, they need a little bit more time. You as the instructor can also jump in and give hints if they're really struggling with it. These are some things that could go wrong. So if we were describing it based on things other than the terminology of the field, like rhymes or homophones, that's not going to work very well. Wouldn't engage with the concepts the way we want. It could go wrong if their description is describing something that is a common misconception, and then the other students are reinforcing their common misconception. That would be a problem. Again, too easy or too hard would be a problem. You may also see, if you're using this too much, that there's the outgoing or quick ones that are just going to throw out all kinds of ideas and really dominate all the conversation. So you would want to build your groups carefully to try with that. Questions or comments on taboo? Thanks for playing. Next one. This is one that I started using in fall, and this came out of the engineering education literature. So first time I did this in class, I did a little bit of debrief afterwards. The students just said, how did this go for you? And they said, absolutely, that was amazing. You should do this a lot. Keep doing it. Okay, I'll keep doing it. So the basic idea here is this works well in classes where there's lots of problem solving going on. So my physics class, that's definitely true. Math classes, that's true. Also true in programming classes, right, Lou? I think it could work in business classes as well. You're doing some problem solving, case study sorts of things might work with this. So the idea here is, instead of just giving students a problem and having them work it out themselves, which is a totally great exercise and you should do it sometimes, instead of that, give them the solution too, and then have them talk through the solution. So they have their printed handout with the actual solution to the problem on it. You divide them into pairs. One student is the explainer, and the other student is the questioner. The explainer explains. They take some portion of the solution on the page and they explain step by step what was done and why it was done. That's a challenging task for somebody who's learning how to solve a problem. As they're doing so, the questioner is asking clarifying questions. Anything that they explain that is not completely clear, they ask a question about that. They also can give hints. If the explainer is struggling and they have other ways to think about it, then the questioner can jump in and do that. But the explainer is the primary responsibility.
Does the questioner have the solutions?
Yes, both of them do. Yeah, so it's not about finding the solution, it's about understanding the solution is really the goal here. So you do this for a few minutes and then you trade. So everybody's getting a chance to explain and everybody's getting a chance to question. I tried to choose a problem that would be somewhat comprehensible to a diverse audience like this. So in your handout, if you've got that up, the last page of the handout, I guess it's the last couple of pages if you're doing it on the PDF, have a problem that I've set up for this. Looks like that. Okay, so here's what we're gonna do with this. I'm gonna try it. I haven't tried this in online before, so it could be interesting. We have 4 of you, right? So I'm gonna take the 4 of you and I'm gonna put you in 2 breakout rooms. One of you is the explainer, one of you is the questioner. And we'll do just one quick round of it. So explain up to the first dotted line on the paper. And then we'll come back from the breakout rooms and see how it went. So it's been a while since I used breakout rooms. I have to remember how to do this.
Wait, Peanut, can you go back? I have the Jamboard. Did I miss the handouts?
Yeah.
It's in your email.
Okay, oh, nothing was attached.
Yeah, exactly, same.
I'll send it to you. Forwarded you the email, but did not forward you the attachment. Okay.
Thank you.
Okay, so let's go one technical person and one non-technical person in each room. So Lou and LaShawn and Edwin and Courtney are going to go into the 2 breakout rooms. I'm going to assign you manually, create 2 rooms. So LaShawn go in that room. Edwin and Courtney go in that room. Okay, 3 minutes.
It's like, I think we should look at page
Okay,
number
so
6,
they-
right?
Yes, page number 6. From the top of page number 6 to the first dash line.
The first dash line, that is basically explaining why the intersection point is 0.92, comma.
Yep.
Oh, okay. Okay.
So who's the explainer here? You get to choose.
Let's go with Lou.
Yeah. So there are 2 equations.
Uh-huh.
Both equations represent a straight line. Each equation is
Yeah, so you get, where do we go here? 2y, yeah, 2y plus 4x. So when y equals 5x minus 3, so that's why that goes into the parentheses. So x equals 13 over 14, and then we'll put that back in the equation. So 5 times 13 over 14 minus 3. I feel like I did this with my 5th grader just not so long ago. Not to undermine the work that we do with our, yes. So yeah, you find both the x and the y, and oh, and we're going to convert to decimal form. Excellent. To 5 places.
I'm okay with fractions.
Oh, good. Fractions seem cleaner a lot of times.
I am too. The fractions are exact and the decimals are not.
Aha, yes. So, yeah. So when you get the x, then you can substitute into the y, and that's where the intersect is at the x comma y coordinates.
So my question is, I think I understood everything that you just said, but like, how does that relate to the graphs and the solution then? Because like the way that you just described seems like it was purely algebra.
All right, I think everybody's back now.
Yeah, I was trying to fake a lot of things with Edwin, but I think I was getting away with it.
You went fast.
I mean, I'm in communication studies, but I'm still a quantitative social scientist. I can look at numbers. I feel great about it.
So that was way too fast to do this activity. If we were doing this for real, I probably would have taken about 20 minutes on this problem. And the big 3 dashed lines broken up into 3 segments on this problem. We'd be changing groups and changing roles, explainer and questioner, and doing 3 rounds of it. You all were fast enough that I didn't need to do that. So how did it feel?
For me, it felt like I can actually demonstrate some vulnerability with regards to not really knowing, not at all sure. I felt comfortable being able to say, I don't understand.
Okay, that's good.
So I have a question, like, in the role of the explainer, like, are they required to use the approach in the given solutions, or like their job is to explain what the solution says, right? So what if they're like, okay, I have a better approach than the solutions, then
Okay, if I was teaching a class and somebody asked me that question during class, I would say, that's great that you've got multiple ways of doing that. Let's have you share back with the class what your other way is.
Mhm.
And of course, this one, there's a million ways to do this problem. This was just one. Okay. When I did this in class, I found that there was lots of students that found the spot where they weren't really quite getting it. And that was really valuable to focus in on those places and shore up those gaps so that then they could go and solve a problem themselves instead of just trying to parse out the solution. We definitely have an issue within lots of these technical fields that it's easy for students to look at a solution and say, oh yeah, I get that. This is taking it to the next step, saying you have to be able to explain it. If you can't explain it, then you didn't really get it. So that prevents that false sense of security that they sometimes lull themselves into.
Yeah, I appreciate that, Peanut. I'll just affirm that. There's a saying that is that to teach is to learn twice. And so when you are articulating what it is that you know in the communication field, I don't know what I think until I hear what I say. And it is even in the nonverbal communication and the confidence with which you explain what it is that you are teaching that you can learn where your vulnerabilities are.
Okay, so the quick comments on this. I think this is really good for promoting understanding of what the process was, in addition to the conceptual understanding that I talked about in the peer instruction. So I use a suite of different things. I'll often start out a unit with peer instruction sorts of questions to get the concepts down. And then I'll shift towards more think aloud pair problem solving to really get the process down. Then I'll set them loose to do group problem solving, sorts of things. Very good at identifying where they're not 100% clear. It shows it very, very well. The time on this really depends on the problem. So this particular problem, we just did in about 5 minutes. If it was a more complex problem, you could spend an entire class period on this. That may or may not be advisable depending on what your goals are for your particular course. Does take about 3 minutes per rotation, so you want to be switching roles pretty frequently so that you don't just have one person coasting while the other one is doing all the explaining. Biggest failure modes on this one, if your solution is not well written, if they can't understand your solution, then they can't describe your solution. I found some issues in some of my own solutions where I was skipping steps that I didn't realize I was skipping, and they would get stuck on those. Oh yeah, I probably should have said that. If the explainer is struggling to communicate, that can be a problem. So this is a more challenging exercise for students who are not as verbally acute. Possibly including second language students may be disadvantaged by this. So I do want to be a little bit cautious with that. And I was just saying that it prevents the sense of false confidence, but it can also give the sense of false confidence because the solution is there in front of them instead of having to find it themselves. So I wouldn't stop with this. this is a step towards getting them to be able to solve their own solutions. This one I'm going to mention specifically. The book that I pulled this from also recommends doing this in a programming sort of setting. So Lou, that might be of interest to you, where you could have one student coding and the other one questioning the coding as they're doing it.
Okay. That's good. Yeah.
Okay, moving along. Handouts with gaps. So this one I'm going to do the gap right now. The handout for this workshop you all have is a handout with gaps. Yes, I'm being a little meta here. So this one I've kind of been doing as we've gone through this whole workshop. The places where the handout has the gaps, that's how I would do it in class. When I get to the gap, I'd write it down. Sometimes I would have the worksheet up and I would write it straight on the worksheet so it looks just like what the students are doing. In this case, I've been often just putting it on the Jamboard. So I would say this is a little lower grade interactive learning, but it's still definitely interactive learning and can work in a lot of settings. You're giving them a handout of the lecture that you were going to do anyway. So it's lecturing, but it's augmented lecturing, because instead of the students just listening and taking their own notes, probably frantically scribing to get everything you wrote down on the board, they're only writing down the things that you put a gap for. So that tends to highlight the things that they really need to be remembering. So as you're doing your lecture, the professor is going to follow along with the notes and write in the gaps. And then the students write in the gaps as well. So what's this good for? It's good for emphasizing key points. It does provide a roadmap. They have the lecture notes right there with them. And instead of spending all their time scribing frantically, now they're thinking more, I hope. It does increase the interaction, but it doesn't reduce coverage. If that's a concern for you, some people say they don't want to do interactive engagement because it reduces the time they can spend on content, so they can't cover as much. But again, I'm not so much concerned about coverage. I'm concerned about learning. It's just not necessarily the same thing. It takes exactly the same amount of time as lecturing. I personally don't use this because I like to improvise a little more in class. And this kind of locks you in. This is the things that you're doing. So that's why I'm actually on the Jamboard instead, because if something comes up, somebody asks a good question, I'll just start a new board and go with it in real time. This could backfire if the students say that filling out the worksheet is what's important, rather than understanding what's going on, emphasizing those key ideas. So be a little bit careful with that. Okay, we got about 3 minutes left. I'm going to hit one more. I'm cruising. Last one is what I call swarm notes. So this is a technique that I personally came up with during the pandemic. So pretty well suited to online learning, and it worked so well, I'm still doing it in face-to-face classes. So the basic idea here is you lecture, preferably while also doing some interactive engagement sorts of things. But instead of writing notes on the whiteboard, I write my notes on the Jamboard, as you're looking at here. One word of warning on that, Jamboard is being decommissioned by Google this summer.
Unfortunate.
October. There are other options that work well. So I've been playing with those a little bit. Lucid Spark is my recommendation for a replacement of it, but I haven't played with it enough yet to incorporate it in the workshop yet. So you use a virtual whiteboard, you take notes on the virtual whiteboard. The students also take notes on the same virtual whiteboard. So instead of my notes, it's a collaborative set of classroom notes. That's why it's swarm notes, because we're swarming these. I use it for many sorts of things as I'm doing class. It's very, very flexible. So sometimes during class, I'll be writing on the board. Sometimes during class, I'll ask the students to write something. Sometimes I'll tell the students will ask a good question. I'll say, that's a great question. Put it in a sticky note, stick it on the board. Any of those sorts of things work well. For more problem solving sorts of things, I like to do the next steps on it. So one student will do a step of algebra, the next student will do the next step, and they collaboratively work it through and solve each other's errors and those sorts of things. So I'm going to give my quick answer to this one. Which of the techniques discussed in this workshop can be incorporated in swarm notes? All of them. So this is kind of like a framework that you can use a lot of. other interactive teaching things in. I love using this because it's a collaborative community. These are everybody's notes and we're working on them together. So if somebody has an idea, they put it on there for everybody's good. They are not scribing, they are thinking, because these are permanent. They have access to them electronically after class is over. So they don't have to write their own notes. I use sticky notes to highlight student ideas and questions. Those things are great. It is good for building this classroom culture of student contribution. Why did I put that as a failure mode? That should be a good for. There's up there. There. It can have technical problems if students are having trouble writing notes. So in some of my classes, I've actually purchased for the class a set of little tablets like this one that I'm writing on. Some of them will bring their iPads and that works well. In larger classes, it may be prohibitive to purchase that sort of tech for them. Sometimes I will see students don't want to write on the board because now they're putting it out there publicly, and there's a fear of being wrong on that. Okay, so that's mostly what I've got. Oh, there's one other thing I was going to mention on this.
Can I ask a question about it?
Yes.
So do you have a blank set of Jamboard notes every time you teach the class?
Yeah, I do.
Okay, so you have basically you share a copy of them with students. Got it. Okay. That's really interesting. I teach a small group communication class, and it is designed for students to work together. They actually take exams together. They have different textbooks. But to make 5 copies of this for the 5 groups in class, I could see that being really helpful.
Yeah, good. Yeah, so my pre-made slides have basically the things that I would have on my PowerPoint in a traditional class.
Yep.
I don't use PowerPoint for a lot of information. I use it for a lot of the peer instruction questions. So I'll pre-build those, and then I also write on it and take notes. Anything that was on the whiteboard, I leave blank on the Jamboard, and then I'll put it in the Jamboard as we go. But anything that would be on my slides in advance of classes on the Jamboard.
Cool.
The one thing that I was going to mention on this as well, because it does still exist after class, students can go back to it. I have seen some students using it to study for exams, and that's a tool that they have, and they'll go back and retake their own notes on things that they're working on. So when it comes to exam time, it's open Jamboard. All right, we are out of time. Thanks everybody for joining. I had a good time. Hopefully you learned something useful.
Thank you. It was actually very useful. I appreciate it.
Thanks, Peanut.
Thanks,
Yes.
Peanut.
See you soon.
You.
See you all around.
All right, see you later, guys.